So I will speak about the polydisc, function theory in the polydisc. And so it means we are looking at an object like this, d to the n copies of the unit disk. And so what I will do is to show to you what kind of analysis one may encounter, and it will certainly be with a personal touch, because it's mainly about what kind of analysis I myself have encountered in this setting. So I will try to illustrate that through four examples. So I will show you 4 examples, and if you start thinking about the polydisc, or you want to know something about the polydisc, the first thing you probably would do is to pick up Rudin's classic book from 1969, which is called Function Theory in Polydiscs. And I give you a quote from the preface to this book. Rudin writes that briefly the object is to see how much of our extremely detailed knowledge about holomorphic functions in the unit disk can be carried over to an analogous situation in several variables, namely to polydiscs. So that was Rudin's starting point for his book. And I thought I would start then by showing you one of my favorites from the book. From Rudin's book, one of the things that he came to, having this starting point to see how things carry over to the polydisc. So that's about boundary values. So the part of the boundary of the polydisc that matters the most is the so-called distinguished boundary, which is the torus Tn. And the radial limit, if it exists at a point W on the distinguished boundary Tn, is given, well, maybe I can use this one, by this expression. So we put in an r here, multiplied by our point W, and we let this r tend to 1. And that is the radial limit if it exists. And u is some function that is defined inside the polydisc.
Sorry, so there is pointer.
Pointer. Okay, maybe that's better, and I can even the green one. Yeah. Okay, I can try that. Right. So that's the radial limit. We multiply each coordinate variable by r, and we see what happens when r tends to 1. And much is the same as in one variable. So the radial limit of the Poisson integral of an L1 function on Tn exists and equals f almost everywhere on the distinguished boundary. And another thing which is the same is that a bounded holomorphic function inside the polydisc has a radial limit almost everywhere on the torus. So that's fine, that's nice. But there is something that does not carry over, and that is the following. Suppose you have some non-negative function, bounded function, on the unit circle. Then there is a bounded analytic function f inside the disk, such that the radial limit of the modulus of this sum, then there exists a bounded analytic function f on the unit disk, such that the modulus of this function has radial limit psi of z almost everywhere. This happens if and only if log psi is integrable. And the reason for that is really quite simple. This is precisely what we need to obtain a harmonic function u written as a Poisson integral of log psi. And this harmonic function in turn has a harmonic conjugate v, and then we obtain our desired function in this way. So it's an easy explanation of why this is so in the unit circle. This argument fails in the polydisc because not all real harmonic functions are real parts of holomorphic functions anymore. We need to require more. We need to require that basically if we write down a Fourier series, say on some polycircle inside the polydisc, then we need to have either only positive frequencies or negative frequencies. We cannot have a mixture. So you can think of in 2 dimensions as the Fourier coefficients lying, or the indices lying in the plane, and you can only have indices there and there. So that is a serious restriction, of course, and that makes it much more complicated. But Rudin is able to handle this situation in a very nice way. He proves the following theorem. We have a lower, this is a definition of a lower semi-continuous function. And Rudin proves that if we have psi bounded and positive, lower semi-continuous, then we can find a bounded holomorphic function whose modulus has radial limit psi almost everywhere on the distinguished boundary. This is not an easy result. It has an ingenious proof, which is completely different from what you see in the circle. It's more algebraic in nature than its counterpart when n is equal to 1. And I just note here that we still obviously must have the same condition here. This is trivial when you have a lower semi-continuous function which is bounded from below, then it's actually which is positive, then it is bounded from below. So the integrability of the logarithm is trivially satisfied. So as far as I know, there is no progress on finding exactly what the condition should be in general. I mean, a necessary and sufficient condition. To the best of my knowledge, this is the best we know about this situation. So that was just an example of how things change, and sort of one of the nice theorems from Rudin's book. That's my example 1. Now, my example 2, factorization. We have, as we have in 1 dimension, we have Hardy spaces. So HP on the polydisc dn for, say, p larger than or equal to 1, we can define as the closure of holomorphic polynomials in LP on the distinguished boundary. Alternatively, we can define HP as those F in LP on the torus whose Fourier series is holomorphic. So means that we only have positive frequencies here. There should be an I there, I guess. And radial limits exist more or less, as I have already said. So we need not to distinguish between F inside the polydisc and on the distinguished boundary. Okay, a very simple and important fact in one variable is that every function f in H1 can be factored in this way, g times h, where g and h are functions in H2. And the reason for that is, and in fact we have more, as I have written here. In fact, we have this equality of norms. And the reason is that functions in the disk can be factored. So any analytic or any function in H1 can be factored as a Blaschke product times a function that does not vanish. And this Blaschke product does not contribute to the norm because it's 1 almost everywhere on the boundary in modulus. So this means that it can be disregarded when we compute the norm, and all we need to do is just to take g to be b times the square root of this non-zero function, and h to be the square root of the non-zero function. And therefore we immediately get this relation between the norms. In general, functions in several variables will not factor or cannot be factored in this way, but operator theory helps us to see what is the right analog. And when I say operator theory, I mean the most important application of Nehari's theorem is that it gives us a statement about Hankel operators, or what I choose to call, or I state these as a result of what's called Hankel forms. So what I'm saying is that in one variable, the most important application of this factorization is to describe Hankel forms, which is defined on H2 cross H2 produces a complex number according to the following rule. We have some function psi, which we call the symbol, and we take the inner product between the product of the two given functions f and g and psi bar. That is a so-called Hankel form. And Nehari, you get immediately from the factorization that h psi is bounded on H2 cross H2 if and only if this symbol defines a bounded linear functional on H1 in the natural way. So we know. So this means that Hankel forms can be characterized in terms of bounded linear functionals on H1. And this follows immediately from the factorization, as I said, of functions in H1. In one direction, the sufficiency is immediate because the product of two functions in H2 will be in H1. And on the other hand, if I plug an H1 function in, I can write it as a product of two functions in H2, and then I see that it has to be. That gives me the necessity of this condition. So when I say that operator theory helps us to see what is the right analog, I mean that we see from this proof that we could run the same proof if we require less. Namely, if we only have that f can be written as a sum products of functions in H2. So suppose we have this, then I can basically run the same proof, provided I have control of norms. So if I have something like this, I have can write f as an infinite sum of products of functions in H2 with this control of norms. Then I can run the same proof. If this holds, we say that H1 admits weak factorization, and we can then introduce an alternate norm for H1, which I call the weak factorization norm. So simply take the inf over these sums where the infimum is taken over all possible weak factorizations. And there is a great theorem by Ferguson-Lacey, that's in dimension 2, and Lacey-Terwilliger in higher dimensions, saying that yes, we can do weak factorization in H1. So Nehari's theorem carries over to higher dimensions. Well, that's very nice. But then that brings me to work of Helsen. This was the last work done by Helsen. Helsen died in 2009, and his last paper was published posthumously in 2010. He asked, well, what happens if we go to n equals infinity? Will we still have a weak factorization? Will we still have a Nahari's theorem? And we can of course define Hankel operators and so on in the infinite dimensional situation, but we can really only just ask the question: what happens with the ratio between the weak factorization norm and the ordinary H1 norm when n grows? And it turns out that this ratio tends to infinity. It grows at least in this way. So the ratio between the weak factorization norm and the ordinary H1 norm grows like, well, this number pi squared over 8 raised to the power k over 2 when we are in the 2k disk. The proof of this result is very simple in some sense, because it's a matter of taking a concrete function and check what happens. And it turns out that for this concrete function, which is a product of these simple linear factors in the 2k variables that we have, this particular function has the property that the best weak factorization we can make is just f times a constant, 1. So in other words, this notion of weak factorization in this situation is sort of deceptive. We do nothing with it. Weak factorization, the best weak factorization is the trivial one. So this is another way of saying that the weak factorization norm is equal to the H2 norm of the given function f. So it's really a function that factors badly. So I will of course not prove this, but once you know that, then of course this is just this number here is just the ratio between the H1 norm of an the H2 norm and the H1 norm of an individual factor like this. So it's a matter of computing the H2 and H1 norm of each of these of such a factor, which we of course can do explicitly. So that was my second example of things that we can encounter when we go to the polydisc. My third example is certain estimates for homogeneous polynomials. And that is rather surprising to me that this is long before Rudin, really long before. It's a work by Bonenblust and Hille from 1931. And the reason I think that it didn't get into Rudin's book is that it takes a completely different perspective. The perspective is not what can we get from the unit disk, but the perspective is we come from infinitely many variables and we need tools to deal with infinite dimensional problems. So we want results which are independent of the dimension, for instance. So let me tell you what it is. It is an estimate that relates the size of the coefficients of a homogeneous polynomial to its supremum on the polydisk. And as I said, it is a result that cannot be captured by Rudin's approach. I mean, this doesn't make sense in the unit disk. Homogeneous polynomials in the unit disk are trivial. Okay, so I will now talk about homogeneous polynomials. I use standard notation here. I introduce multi-indices, and z to the alpha means this, z1 to the alpha 1, and so on. And the degree of the monomial I declare to be this number, sum of the entries of the multi-index. So a homogeneous polynomial is a polynomial of this form. It's an M homogeneous polynomial. The degree is M. And we are interested in that, of course, because it's quite useful to express general holomorphic functions in terms of homogeneous terms. Okay, so the Bond-Hill inequality estimates the size of the coefficient measured in terms of a suitable LP norm against the supremum of the same polynomial with a constant that does not depend on the dimension. So let me, to introduce it, let me start with something obvious. If we take the square root of that, of the coefficients, this is the H2 norm, the L2 norm on the distinguished boundary. So clearly the L2 norm is bounded by the L infinity norm. So this is an obvious inequality. But what I'm asking is, if we now restrict to M homogeneous polynomials, is it possible that we could have a smaller p on the left-hand side, p instead of 2, and still have a constant here, which does not depend on the dimension? We allow it to depend on m, but not, on the degree, but not on the dimension. If p gets smaller, then the norm on the right-hand side gets bigger. And what Bond and Hille proved was that yes, this is indeed possible. We can do that, and we can do it precisely down to p equals 2m over m plus 1. That's the smallest possible p for which we can do it. Once you know that, of course, you are interested also in knowing the precise constant. I will come back to that. So, what does it say? Had the homogeneous polynomial been, the modulus of the polynomial been constant, then we could not have done this. So basically what it says is that if we have a polynomial with, say, many non-zero terms, it says something about the variation of the modulus on the unit circle. So when you think about it, it's perhaps not so surprising that the degree m, which sort of says something about the variation of the polynomial, is related to this, and that we can do it independently of n, perhaps. It is a quite remarkable result, I must say. To see why p is the best, well, what one can do is to look for as flat as possible homogeneous polynomials with many non-zero coefficients, all unimodular. So then you can use some standard, well, let's say some standard tools to find polynomials like that, and that's exactly what Bond and Hille did. I guess they basically invented things that later became known as Rudin-Shapiro polynomials, which are polynomials that are as flat as possible. So that's a way to see that p is best possible. Simply construct polynomials like that. Rudin-Shapiro is the name for polynomials of that kind that were constructed by Rudin and Shapiro in the 50s. But the point I want to make here is really perhaps the most important idea in the work of Bond and Hille. The most profound insight, I would say, is that in order to deal with this, you should go from homogeneous polynomials to multilinear forms. And this procedure of going from polynomials to multilinear form is known as polarization. So this was invented actually by Bonneblust and Hill in this paper. And it's easier to work with multilinear forms than with polynomials. And it seems to be an indispensable tool for proving the Bonneblust-Hill inequality. So then let me say a few words about this business with multilinear forms. This is a work by Littlewood that preceded Bonneblust and Hill. So we are looking at Littlewood looked at bilinear forms on Cn cross Cn, and let here EI be the canonical basis in Cn. So if we take the coefficients of this bilinear form with respect to this basis, take the 4/3 norm of the coefficients, this sequence of coefficients, then Littlewood proved that this is bounded by a square root of 2 times the supremum of the form, where Z and W vary over the unit polydisc in Dn. And this was the inspiration for Bonneblust and Hill. They extended this to multilinear form with M replacing 2, and with this P here, as we've seen before. There is one thing I would like to add here, and that there has been quite a bit of activity in recent years improving this constant, and it seems now that it has been established that it does not grow exponentially, but it grows in fact polynomial in M. And I have seen the claim that this has some importance for quantum information, but I am not able to tell you much about that. So anyway, this is an inequality that still people care about a lot. So anyway, let me just mention how we get to how the relation is between these forms and the polynomials. In one direction, it is clear. If I start with a form, I can easily produce a polynomial simply by putting in the same set in each of the for each of the vectors in the form. That gives me a homogeneous polynomial clearly, and the degree will be M. In the other direction, what we can do is write up a formula. And this is what Bonneblust and Hill did. They had a slightly different formula, but essentially the same. So we take our polynomial, P. We plug in here the following argument, which is a linear combination of the M vectors that we have. And the coefficients here are just points on the unit circle. Okay, so we integrate this against this product, against here normalized Lebesgue measure on the torus. And for reasons that you will soon see, I divide by M factorial in front. This gives us a multilinear form because these products will only give us something when we multiply by a product here involving zeta 1 up to zeta m. So in other words, higher order terms will not get into will not be present in the when we have done the integration. So in other words, it will have to be linear in each of the vectors here. So it is linear, and it is clearly symmetric. And the only question is, do we get P back when we go in the reverse direction? In other words, if I go back using the same procedure as I did before, putting all the z's here the same. Well, to see that, what you do is you plug in then this vector that you get, use homogeneity, which means that this thing comes out as a factor, z1 up to plus z2 and so on up to zeta m to the power m. That comes out. So what you need to do here is to integrate this factor against this product. And again, by orthogonality, the only term you need to care about is the term with the product zeta 1 up to zeta m. And you sit down, compute, and see that the coefficient is m factorial. That's why we had the m factorial there. So that's what they did. And immediately you get from that also an estimate, which is something we really want to have. We get an estimate between the infinity norms of the two objects. The form, the infinity norm of the form, is bounded by this factor times the infinity norm of the polynomial. This is just by, I wrote it here. You just see that this linear combination of the vectors will in fact lie in the larger polydisc m times d to the n. Again, by homogeneity, when you plug this in here, you get m to the m in front of the subnorm of p, if you just go in and take subnorm through the integral. So that's how you get the m to the m. It comes from the m there. That gives you the m to the m down there. And m to the m over m factorial is less than e to the m. So the inequality is what people call in this business hypercontractive, which means it grows exponentially with m. So in fact, and this is a recent result that I was involved in proving, it turns out that the Von-Hill inequality for polynomials, for homogeneous polynomials, is also hypercontractive. So the constant you can put here grows at most exponentially. I don't know if this is best possible. It would be very nice if it could be made even smaller, but for most applications this is good enough, and it gives fairly sharp results in different settings. Okay, so let me mention, before I continue to my fourth example, what led Von-Hill and Hille to do this work. Their motivation was a problem that Harald Bohr had stated about Dirichlet series. So a Dirichlet series, that's a series of this form, an n to the minus s, and we sum over the positive integers. And Harald Bohr was interested in the convergence of Dirichlet series, and the convergence of Dirichlet series is well, it's more complicated than convergence of power series. So if we have a Dirichlet series of this form, then we will have in some half plane to the left of this C here, the Dirichlet series converges conditionally. To the left of this vertical line, which I have denoted B, it will converge uniformly. And to the right, if I said left, I meant right. It's to the right, to the right, and to the right of this vertical line A, it has absolute. It converges absolutely. And these three lines may be different. And Bohr was interested in finding out the relation between these lines. So you can easily see that A minus C must be between 0 and 1. You can in fact achieve both 0 and 1. But the most interesting quantity is the difference between A, which is absolute convergence, and B, which is uniform convergence. And Bohr proved that it does not exceed 1/2. But he was unable to exhibit even one example such that A minus B is positive. Toeplitz managed to get 1/4, and then von Blust and Hille solved it completely in this work that I have been discussing. So what Bohr had, he wasn't able to solve the problem, but he had the fundamental insight that a Dirichlet series like this should be thought of as a power series on the infinite dimensional polydisc. Namely, you take Pj is now the j prime to the power minus s. You map that to Zj, which is now a coordinate function on the polydisc. This is called the Bohr lift. Doing this, we can view the power series, this Dirichlet series, as a power series in infinitely many variables. And that was the starting point for the von Blust-Hille approach. So they had this insight of Bohr to begin with, and starting from that, they were able to use their methods to solve this problem. Okay, so now I made a picture of my talk so far. So we have the disk, we have the Rudin idea. Let's see what we can carry over. But we also have the von Blust-Hille approach or idea that we come from infinitely many variables, and we prove things here which are useful in the infinite dimensional setting. Of course, here results go in both directions. And you might say that Helsen really operates along this whole line. And then, of course, you had Bohr, and Bohr is an important person here because he started with a problem in one dimension, apparently, Dirichlet series, but he realized that we should lift this to the infinite dimensional situation. And that was actually the first work, I would say, serious work, one might say, on function theory in polydiscs. Okay, now my fourth example. Greatest common divisor sums from Poisson integrals. Well, here I have written down the Poisson kernel in one variable on the unit disk. So W is a point in the unit disk. And let me also here, I have written down explicitly the normalized Lebesgue measure on the circle. Then we know that if I plug in here an L1 function, I obtain a harmonic function whose radial limits coincide almost everywhere with f, as I say, f is integrable. And now I use this formula for a very simple function. I take simply an exponential, z to the n, and I choose the point w equals r. Well, then this formula, of course, gives us the value r to the n, and it doesn't matter if I take f of z or f of z bar, I get the same. These are harmonic functions. Well, that's very simple, but it becomes more interesting if we lift this to the polydisc. This is just a more elaborate way of writing it. I take the inner product between Zm and Zn against this Poisson measure, and then I get the same thing, of course. Now I lift it to the polydisc. Okay, so I take the Poisson kernel on the polydisc. It just means I take a product of one-dimensional Poisson kernels. for what will come now, we should think of the W here actually as a point on the infinite dimensional polydisc. It just means that W is a sequence, and I pick the K first terms in this sequence. Okay? Okay, we must use, or we use again multi-indices. So we can think now of multi-indices as infinite sequences, but we stop at K here. So we have non-zero values up to K. So we have beta is a multi-index, mu is a multi-index. And I declare the absolute value of beta minus mu to be the absolute value of the difference beta 1 minus mu 1 at each entry of the multi-index. Okay, well, then the formula that I had in one variable becomes this on the polydisc. R to the multi-index beta minus mu. R is now a sequence. So this is multi-index notation for raising R to the power the first index times the second, and so on. Still, it is well, it gives us the following lemma, which is quite interesting. For a positive sequence, let's say in the infinite dimensional polydisc, you take arbitrary multi-indices, then this you can call it matrix, defines a positive, is a positive definite matrix, and it can be written explicitly as a Poisson integral in this way. This is just rewriting what we had on the previous slide. Now, let us relate this to integers. So we let now P be the sequence of primes. Okay? And then, of course, we know that we can factor in integers, so we can write an integer in multi-index notation. N is P to the beta. Okay? Any integer can be uniquely associated with a multi-index in this way. So then we can, well, use a little algebra, and then we can see that if we choose as our R 1 over P, I mean we take the reciprocals of the primes, then P to the minus this difference between the two multi-indices becomes this expression, right? Because A plus B here, that corresponds to the product of the two integers, and this corresponds to the greatest common divisor. So suddenly our Poisson integral becomes a statement about a sequence of integers. We can also allow, instead of just taking the reciprocals, we can raise all primes to some positive power, and we get a class of matrices of this form. So I'm just translating now the statement I had before. I put all the C's that was in the quadratic form equal to 1. So it means I plug in just this polynomial, and I choose then some. Given these capital N integers, beta j simply corresponds to the multi-index from the prime factorization of n. Okay, so this means that this sum, which I call a greatest common divisor sum, can be written as a Poisson integral in that way with respect to this polynomial with these degrees coming from the integers. And, well, people are interested in computing how large sums like this can be. And there is an old, yes, and let me just introduce notation here. We divide by n because that's quite natural to do, and we ask how large can it be. We take the soup over all possible n tuples, capital N tuples of integers. How large can this sum be? Call that gamma sub alpha. This problem goes back to Erdős. Erdős posed the problem of estimating sums like this in 1940, and Gall showed that if you take alpha equals 1, that means reciprocals of the primes, then you get precisely log n squared. Well, up to constants. And Gall's proof is very much a combinatorial proof, and it seemed very difficult to extend that to other alphas. So it seems that if you want to do it for other alphas, and there are good reasons for doing it. I mean, these estimates are used in different contexts. So in order to deal with this more general situation, it is very useful to go to the polydisc and do estimates in the polydisc. But I would stress that the game is now sort of a combination of estimates in the polydisc and the combinatorial arguments coming from Gall. So it's a rather interesting combination of combinatorics and the polydisc. So as you see, quite recently I did this work with Eisleitner. We got essentially sharp estimates of these quantities gamma sub alpha for essentially all alphas. There is a possible problem here that there is a log-log factor too much, but otherwise this is as good as it can be. And as I say, there are good reasons that people are interested in this. They are used in the Fontaine approximation and also to study systems of dilated functions, almost everywhere convergence and things like that. Okay, so I'm done with my 4 examples, and I just summarize what I've said. Rudin's example hopefully show you that classical results on the disk leads to new problems on the n. Well, it was done in 1969, but still. I tried to convince you that there is interesting interaction with operator theory with these Hankel forms. The infinite dimensional viewpoint leads to problems that you cannot see in one dimension. And finally, the subject interacts with number theory and other fields. Thank you.